Well, actually, I had a teacher in high school. Pretty much everybody has a teacher in high school who was excited about mathematics, and my teacher is mentioned in my book as Mr. Grant. He was doing an experimental course. The experiment apparently was considered a failure because it was never reproduced. But he was really, really enthusiastic about it, and he paid it, and he was kind of eccentric. So a lot of the other students made fun of him, but he was so sincere and so so committed to what he was doing that I couldn't help but feeling sympathy for him, and he supported me all through my years at high school. Sponsored my senior math project, and don't know whatever happened to him, unfortunately. After that, when I got to Princeton, very foolishly, I thought I was interested in number theory. For some reason, I was interested in number theory. There was a course in number theory. Another individual, because there's absolutely nothing to do in Princeton. I don't know if you've ever been there, but if you go there, you'll see there's nothing to do other than work. And I decided to take the course in number theory. I was not at all prepared, but the teacher, whose name was Walt Hill, as I said, there's nothing for him to do. He was a first-year instructor. So after the class, which took place in the evening, he would sit with me and explain what it was I was supposed to have understood. And this would go on for an hour, and one way or another, this just became a routine. So that's how I ended up getting into number theory. At a certain point, and I think maybe this answers the question, this is also mentioned in my book, he was explaining, in addition to explaining what was in the course, he was talking about the kinds of mathematics that interested him. So he told me about We's proof of the Riemann hypothesis for curves. And at a certain point, he said, well, you're counting the points on a curve, and then you use Lefschetz fixed point formula. I said, that's really unexpected. I had heard about, when I was in high school, thought I was interested in topology. There wasn't a course in topology. That's why I took a course in number theory. And I thought, wow, if you can use something so unexpected to answer a question that in some sense has been around forever, wow, that really struck me, and it stayed with me, I believe. If Walt Hill had not taken those hours after class to explain what was going on in his course, I probably would have ended up being a molecular biologist, nevertheless. Well, I just explained that I could have been a molecular biologist. When I was, as I said, I took a break in graduate school to read a lot of philosophy, and I thought there was more meaning to that. Then the other thing, apart from the fact that the career path was not clear, the more I read of philosophy, the more I realized that academic philosophy was was going to provide no more enlightenment as to whatever it was I thought I was looking for than mathematics. So I was fine doing what I was comfortable with. The easiest thing to say, which is not necessarily the most accurate, is that I'm working. Well, I suppose it's accurate to say that I'm working within the framework of a well-defined research program. I'm doing my part to advance this program, like most of the people here at this conference, which is the Langlands Program. And it has many different branches and ramifications. One can go to 5 different conferences on the Langlands Program and not see the same people at any 2 of them because it has so many different aspects, and it keeps growing. But the interest of the Langlands Program is that, the way I got into it, partly as just a wave, I arrived in graduate school. At the end of my graduate school, it became standardized. There was a 4-week meeting in Oregon, famous meeting, which most of my contemporaries attended, that set out the parameters and the goals of the Langlands Program. And so it's almost as if it were strategic planning, well defined because the people who organized it, especially Armand Borel, had a very, very clear ideas of what should be done. And then it just keeps advancing, and the goals are, the major goals seem to be as far away as ever, but intermediate goals do pretty well, and there's always something new. So that's what I do. I've been working in the Langlands program off most of my career, and related questions, because I also started out as a number theory. Langlands program is not only number theory; it's also other branches of mathematics, and not all of number theory is encompassed within the Langlands program. So I've been trying to stay at the border. I wouldn't say it's so spectacular. It's quite modest, actually. Langlands himself, when he talks about his program, is always insisting on how little is known. He's been doing that ever since he started, and on the modesty of his own contributions. And I think it would be totally inappropriate for me to claim to have done anything spectacular. Probably, if you were to ask somebody in the field what I did that makes me a suitable candidate for being interviewed, I would say the answer would probably be that with Richard Taylor, we gave the first proof of the local Langlands conjecture for GLN. That's something that can be pointed to. I got into that quite unexpectedly. It was a detour that I had not anticipated, and at the same time, it's problematic to say that I'm responsible for this, because I came in in the middle, maybe even not in the middle, after quite a lot had been done, and my work, first a few papers of my own, and then the book with Taylor, were a small part of the local Langlands program, which is still going on. But in any case, it's conventional for some reason, and there's an important aspect of mathematics. It's conventional to mark a turning point, or not even a turning point, but a conclusion of a direction in research by the names of the people who happen to be there at that time. So that's one thing. The other thing would be, I suppose, the Sato Tate conjecture also with Richard Taylor and two other groups of people in two stages. And that's a conjecture that is an application of some insights of the Langlands program to number theory. Once again, we were looking for something else, and this more or less happened to be in our way. It was a direction. It took some years to finish it, but the decision to work on this happened essentially in the space of 5 minutes in 2000, and then it took 6 years to get to the first stage, and then a few more years to finish that. So but again, Langlands himself would insist, and I have to agree with him, that this is something. It's somewhat illusory to think of this as a natural stopping point. It just happens that there are methods available to get this far, but the real problems, what Langlands would see as the fundamental problems, are still as impenetrable as ever. No, I'm not going to describe that. I think I already explained that when Walt Hill told me about the Lefschetz fixed point formula in Wei's proof of the Riemann hypothesis for curves, that was a great revelation. But instead of talking about that, let me tell you about a dream I had that is what got me in the direction of the local Langlands correspondence, because I had not been thinking about this, but I went to a thesis defense that was related to this question, and for some reason I woke up the following morning I had an idea, and the idea was totally unexpected, but it was actually related to this very same use of the Lefschetz fixed point formula. And I thought about it, and it didn't actually work out in the way I had expected, but somehow, because it didn't work out as a kind of consolation, I somehow found a way to get started on the local Langlands correspondence. But I very much liked this. I really liked it. In some sense, I really would have preferred to have finished the idea that came to me in my dream, because, you know, it's as I say, so unexpected. I wouldn't even go so far to say that it's philosophically naive, because they seem not to be aware that philosophical questions, many of my colleagues, especially my more distinguished colleagues, seem not to be aware that philosophical questions can be raised at all. On the other hand, philosophers who write about mathematics seem not only not to know, for the most part, but there are some important exceptions, but seem not only not to know very much about mathematics, what mathematicians do, but also not to care, and even to think that a philosopher who does care about what mathematicians do is on the wrong track and probably ought not to be a philosopher at all. This, by the way, goes back, you can trace this back to the very earliest Greek philosophy that deals with mathematics. So I've been interested in this. Maybe because I did spend that semester reading a lot of philosophy. It's not that I know more philosophy than many of my colleagues, because many of my colleagues know much more than I do, but maybe I just have a lower threshold for annoyance, for irritation. I guess another point is that I feel that that mathematics is profoundly contingent. One wants to talk about mathematics as something natural and unchangeable, eternal. And in fact, one can't. That's not a defensible position. It's because if it were true, then of course human mathematicians would be redundant. At some point, some machines would be able to find these eternal principles better than the humans, and then that would be the end of that. And I don't believe that. I think mathematics is a form of human experience. It only makes sense as something that human beings do, and that's a matter of some concern, because some of my esteemed colleagues are despairing of merely human mathematicians, the ability of merely human mathematicians to verify, to confirm, to certify mathematical discoveries, and are looking for guidance from machines. And I think that's totally wrong-headed and perverse. But that's another reason it's important, I think, to think about philosophy, because if one doesn't examine the implications of one's position, then one can easily be misled. Well, I think that the United States is just so wealthy that it's not good, and such, in spite of many flaws that are on display, particularly during this election season, it's still very open in a way so that inevitably there will be, as long as there are universities, as long as there's research, there will be mathematics in the United States. France, I'm not so keen on this claim that France has the highest number of fields. It's first of all, the counting is a little bit off, because anybody who happens to take French citizenship at some point is counted as French, whereas the people and there's quite a few of them, have taken American citizenship, somehow don't get counted among the Americans. It's also, but more to the point, I think it should be a matter of concern that I've met a French fields medalist in Switzerland and another one who was claimed as French fields medalist in Chicago, and they're very happy there. Just yesterday, I read an article in the an op-ed piece in the Monde, signed by 7 Nobel Prize winners and Cédric Villani, the fields medalist, who was courageous enough to continue to fight for mathematical research in France, and they were concerned about the deep cuts in education and research budgets. And I think that there's no doubt that France has a very strong mathematical tradition. It was the first. Well, in the Enlightenment, France got a head start on all the other European countries. And then there was a period when France was somewhat outclassed by Germany. But since the Second World War, there's no question that France has been the dominant mathematical center in Europe, especially Paris. There's nothing like Paris anywhere. But if these fields medalists plus the Nobel Prize winners plus the fields medalist pointed out that there's been a cut this year, and this is not the first year of cuts. 134 million euros in this research budgets, the main research institutes. Well, if this continues, and this seems to be the pattern across Europe, I don't think that France will have to worry about its tradition much longer. Education in France, at least theoretically, is much more egalitarian. Public education in France is much more egalitarian than in the United States, and the higher salaries at our universities in the United States mainly go to pay for private schools for professors' children. That's something of an exaggeration, but it was very disturbing to discover after moving to France that French public education, at least in the big cities and certainly in Paris, was moving in a highly inegalitarian direction, so that you were assigned to your college on the basis of your neighborhood, but then the cost of housing was very strongly correlated with the future prospects of the students who attended the local college. And I think it's, when I was a student, it was not so unusual to go into the sciences, into mathematics, coming from a rather modest background like my own. I think that's much rarer now. It's still possible, if you happen to be the child of a school teacher in France, to have an advantage, to be able to get into the elite schools. But and if you don't go to the elite schools, it's very, very difficult in France, especially the École Normale Supérieure Rue d'Ulm. It's very, very difficult to continue in a mathematical career. Now, in the United States, teaching at Columbia University, they make an effort. They make an effort to offer an education also to students of modest backgrounds. But one sees that the people who go on even in the sciences are disproportionately coming from rather affluent families. It's interesting, the last lecture by Jim Arthur was on Langlands' program for continuing, for reaching his final goal. So he has a vast, extremely elaborate program with many predictions, some of which would apparently be unexpected, that have been, he stated his program in its first form around 1970 or just before 1970, and then it was refined over the following decade. As I said in this conference at the end of my graduate school in Oregon, the outlines had mainly been established, but how to get there. Over the next century, actually Langlands believes that it wouldn't necessarily take all that long if people just enough people put their minds to it. My feelings that that may be true, it may not be true, there may be some other unexpected idea. But history teaches us that by the time the solution to a long-standing problem becomes clear, concerns will have turned to something else. So I can't anticipate, it's in the very nature of things that I can't anticipate what people will be thinking about when and if the solution to the Langlands program ever comes into view, because the Langlands program itself is being absorbed even as we speak. It's being studied, as I said, by people in many other fields, including physics. 10 years ago I came, and there was a great deal of excitement among mathematicians as well as physicists because Edward Witten had, together with Anton Kapustin, had found a way to fit the geometric Langlands program, which is just one of the aspects, into string theory. And so that's, one has to expect that one doesn't really have any sense of what people are going to be thinking about 100 years